Welcome to the listening section of the TOEFL mock test, brought to you by Spinta. This section measures your ability to understand conversations and lectures in English. In this section, you will listen to several conversations and academic lectures. Each conversation and lecture is followed by a number of questions. You will hear each conversation or lecture only one time. You may take notes while you listen. You may use your notes to help you answer the questions. Some of the questions will replay part of the audio for you. Answer the questions based on what is stated or implied by the speakers. You must answer each question before moving on. You cannot return to previous questions in this section.
Good morning, everyone. Today I want to talk about ocean acidification and why it matters not only for marine life but also for human economies that depend on the sea. Ocean acidification is a change in the chemistry of seawater that occurs as the ocean absorbs excess carbon dioxide from the atmosphere. When carbon dioxide dissolves in seawater, it forms carbonic acid, which lowers pH and reduces the availability of carbonate ions that many organisms need to form shells and skeletons. This process may sound technical, but the biological consequences are straightforward. Calcifying organisms such as mollusks, corals, and some plankton struggle to build and maintain their calcium carbonate structures when carbonate ion concentration decreases. I will outline the mechanism of acidification, give specific examples of affected species, discuss potential ecological cascades, and end with real-world economic impacts and possible mitigation and adaptation strategies. First, the mechanism. The ocean is a large carbon sink, but its buffering capacity is limited. As more carbon dioxide is taken up, the seawater pH declines and the aragonite and calcite saturation states fall. Aragonite saturation is a technical term, but you can think of it as a measure of how easy it is for organisms to precipitate calcium carbonate. Lower saturation makes calcification more energetically costly. Now, specific biological examples. Pteropods are small planktonic snails, often called sea butterflies. They have thin aragonite shells, and laboratory experiments show that under low pH conditions, shells dissolve and survival drops. Pteropods are important prey for fish like salmon, and for many seabirds in polar and subpolar ecosystems, so their decline can ripple up the food web. Coral reefs offer another example. Reduced calcification slows reef growth and combined with warming-driven bleaching. The result is weaker reef structure and loss of habitat for thousands of species. A concrete case that links biology and economy is the shellfish industry. In the early 2000s, hatcheries in the Pacific Northwest experienced high larval mortality that was later linked to more acidic coastal waters during sensitive developmental stages. In the Pacific Northwest oyster industry, we have seen hatchery failures linked to changes in pH during critical larval development. Those failures translated into huge economic losses for growers and local communities because oyster production is labor-intensive and regionally concentrated. So ecologically driven changes can have clear socioeconomic consequences. Fisheries and aquaculture rely on healthy base species, and any reduction in productivity cascades into reduced catches, higher prices, and loss of livelihoods. We should also consider interactive stressors. Pollution, nutrient runoff, and warming can exacerbate the effects of acidification, or in some cases mask them by changing local carbonate chemistry through increased biological activity. Looking forward, models project continued decline in pH and carbonate saturation globally if emissions remain high. But there is variability among regions due to ocean circulation and local processes, so impacts will not be uniform. What can be done? Mitigation at the global scale means reducing carbon emissions, which is the ultimate control on ocean chemistry. At local and regional scales, managers and industry have more immediate tools. Monitoring networks can detect harmful conditions. Early water quality controls that reduce nutrient runoff help, and some hatcheries have used buffering systems to stabilize pH in rearing tanks. There is also research into selective breeding for more resilient bivalve strains and into restoration strategies for reefs that incorporate acidification projections. It is important to emphasize that adaptation options can buy time, but do not replace the need for large-scale emissions reduction if we want to avoid the most severe long-term impacts. In summary, ocean acidification alters seawater chemistry in ways that challenge calcifying organisms can restructure food webs and carries economic risks for fisheries and aquaculture. Understanding these links between chemistry, biology, and economics is essential for designing effective conservation and management responses. Thank you, and next week we will examine the methods used to monitor coastal carbonate chemistry and how those data inform policy decisions.
Listen again to part of the lecture. Then answer the question.
In the Pacific Northwest oyster industry, we have seen hatchery failures linked to changes in pH during critical larval development.
For more TOEFL mock tests, as well as IELTS and Cambridge practice, visit www.spinta.org. We provide updated tests every single day, AI feedback for your speaking and writing responses, and access to a wide range of high-quality mock tests to help you prepare with confidence.